Hello and welcome to another Neural Net Makers tutorial. Here we're going to be talking about variables and how to represent them in several different systems of notation. The two main systems of notation we're going to focus on are matrix calculus and array calculus. Not many of you may have heard of array calculus since it's essentially a term of my own invention, and it's essentially an offshoot of tensor calculus that gets rid of some of the more complicated and unnecessary aspects of tensor notation for our purposes. Okay, so let's talk about variables in matrix calculus. First off, there are three kinds of variables in matrix calculus. The first type is scalar variables. These don't have any indices because there's only one element in a scalar. The second kind of variable is vectors. Vectors only have one index and have multiple elements. And last, there are matrices. Matrices have many elements that are indexed by two indices. For the purposes of this tutorial, I'm assuming that you have a base level knowledge of scalars, vectors, and matrices from whatever courses you took in college or high school. We're only recapping this because it's important to refresh your memory on these objects. We are going to actually be using them in a slightly more specific way than you have probably been taught. The first important lesson in matrix calculus is that everything is a matrix. And the first place we'll see this is in our treatment of vectors. Vectors are either row vectors or column vectors. By default, vectors should be assumed to be columns unless you're told otherwise. For the purposes of matrix calculus, a row vector and a column vector that have the same elements are not equal. In order to make them equivalent, we need to use a transpose on one or the other. So now let's talk about expressing the size and shape of our variables. First, there's the notation that you're all familiar with. If you have a 5x3 matrix, you'll indicate next to the variable that the first dimension has 5 elements and that the second dimension has 3 elements, with an x in between. Next, we're going to introduce the Tucker notation, which many of you are most likely unfamiliar with, which is sad because it's actually a wonderful notation for helping people intuitively use matrices and apply algebra to matrices. Here, if we have the same matrix, 5x3, we're going to represent the size on the lower left side for the column dimension, so a 5 will go there. And on the row dimension, we will indicate a 3 on the lower right-hand side. Remember multiplying matrices and how the inner dimension between two matrices had to match? Well, in Tucker notation, there's a more elegant way to represent this. When the dimension shared between two matrices matches, and they're multipliable, you simply only write one of their dimensions, like this. This tool becomes a simple and elegant check step to see if two matrices are even multipliable in the first place, or if you're handling them correctly. If used correctly, matrices become a little bit like Lego bricks in that they snap together in specific patterns. Now let's talk about a really important matrix that we will use quite frequently in these courses. This matrix is called the identity matrix. We always represent it with the bold uppercase letter I. The identity matrix is a very simple matrix in that its structure is readily apparent by a very simple equation. For example, if we have an identity matrix with the index I and j, when I and j are equal, that element will be 1. When I and j are not equal, that element will be 0. Further, identity matrices will always be square matrices, square and symmetric. Given what we just learned, if we had a 4x4 identity matrix, it would look just like this. Please make a note here that we are omitting elements that equal 0. The term identity is a more general term that refers to a value for an operation that when two values are operated on, it returns the other value. So for addition, for instance, the identity is 0. When you add 0 to another number, you get that other number. The identity for scalar multiplication is 1. When you multiply 1 by another number, you get the other number. Similarly, in matrix calculus and linear algebra, the identity for matrix multiplication is the identity matrix. When you multiply any matrix by its appropriate identity matrix, you get the original matrix. Now it's time to talk about variables in array calculus. At first, this is going to seem surprisingly similar to index notation, but that similarity is somewhat deceptive. In array notation, everything is an array. Arrays can have any number of indices. Unfortunately, the number of indices an array has will often be called the rank. In tensor notation, this is called the tensor rank. This is a little confusing because in matrix notation, rank refers to something different. So if it's less confusing, you can refer to the rank of a tensor as its order, which is also a common way to denote how many indices it has. So in array notation, a scalar is just an array of order 0. It has no indices because it has only one element. A vector is an array of order 1 or rank 1 because it has one index. And a matrix is an array of order 2 because it has 2 indices. Going further, you can make an array of order 3. So this has 3 indices. Anything beyond order 2 arrays tend to be best represented in array calculus or some form of tensor notation. Representing objects like these using matrix calculus will oftentimes require minor bookkeeping tricks in order to keep everything of order 2. Sometimes with array notation we'll use upper and lower indices like so. But for us, they won't change the meaning of the variable. Sometimes we'll use them to denote special things when taking derivatives. We'll talk more about this later. Multiplication with arrays are a little different. Imagine the matrix example. A times B. A is a 2 by 2 matrix and B is a 2 by 1 matrix. The result is C, a 2 by 1 matrix. Let's show the elements of these matrices and the system of equations for the result, C. If we look at it carefully, how might we write that in index notation? Let's give A 2 indices, I and J, and let's also give B the index J. When we do that, we can rewrite the equation like this. Now we index each element of the resulting matrix C by the index I. You should take a moment to check over this yourself. In array calculus, anytime an index appears twice, it is already assumed that we will sum over it. So now we can rewrite the equation we just wrote as this. This shorthand is called Einstein's summation convention, and it is common to array calculus and tensor calculus. In fact, it is the most noticeable difference between this notation and most other forms of representing multidimensional variables. Let's dissect it a little bit further. The blue indices are called free indices. This is because you are free to set them on either side of the equation, and they will appear on both sides of the equation. The green indices are called live indices. These indices will be summed over and will not appear on the left side of the equal sign. This operation is called an array contraction, as we are contracting out the index j. In good multidimensional array math packages and programming languages, these operations will have some form of analog, or they can be easily created. Now let's talk about the identity for array multiplication, called the Kronecker delta. It's usually represented by a lowercase delta. The Kronecker delta will have pairs of indices. Each pair of indices will be made up of an upper and lower index. Here's an example. Similar to the identity matrix, when this Kronecker delta's pair of indices is equal, that element will equal 1, and when the indices are not equal, that element will equal 0. Importantly, the index A and B must be of the same length, in order to make sure that this is essentially a square object. Going further, Kronecker deltas can have more than one pair of indices, like this. In this case, A must equal B and C must equal D for the element to equal 1, otherwise the element is equal to 0. We will see why this seemingly arbitrary structure is so important soon. Hint, it has to do with derivatives. But for now, let's see what happened when we multiply the Kronecker delta by another matrix. Here's an example. Let's break it down. Again, we have the live indices in green and the free indices in blue. Again, the live indices get contracted out or summed over, while the one free index is left both in the left and right sides of the equation. Functionally, it seems like all we did was rename A's index from I to K, and that is in fact all that happened. For this reason, sometimes the Kronecker delta is called an index juggler because it renames indices. In general, array notation allows for index names to be changed almost arbitrarily for convenience. What defines an index is its order with respect to the other indices, not its name. This is probably the hardest part of array notation and tensor notation for most students to grapple with. Right now, the Kronecker delta may seem meaningless or worthless, but it's anything but. Later you'll see that the Kronecker delta literally tells you how to simplify really complex equations, when those simplifications are really hard to see in other forms of representing the equation. You won't typically see them in the finished form of an equation, but you will use them all the time when working through one. Okay, that wraps it up for this part of Lesson 1. Next time we will introduce our first neural network and look at a method for training it, and we will examine the general paradigm for training neural networks.